Okay, we're going to look at activation energy, and we have looked at potential energy diagrams. And a potential energy diagram shows the energy pathway that happens in a chain, in a reaction. As I say, a chain of reactions, and it can be when we looked at Hess's law, but in a reaction. And so, if it's exothermic, remember that we see a step down. So here's our reactants, and here's our products requiring less energy. Uh, and in endothermic, we see a step up where it requires more energy to form the products than it does the reactants. Okay, so this is potential energy diagrams. We're going to expand on those types of diagrams, and we're going to add a whole bunch of labels to a diagram. So some of the things that we know from Chem 20, in Chem 20 we knew that all atoms were in motion, and so all reactants are in random motion. And so before a reaction starts, those reactants have kinetic energy because they're in motion. Kinetic is energy in motion, whereas potential energy is the energy waiting for the motion to start. And so all chemicals also have some potential energy because of the intermolecular bonds between forces, or between molecules, particles. We also remember, if you look at Chem 20, when we were doing gas laws, we looked at the KMT, which is the kinetic molecular theory. So a chemical reaction has to involve a collision between the reactants. It's just not a matter of a passive reaction. Two things, they have to collide, and when they do collide, in that very brief moment, there's no kinetic energy. And then when they form one entity, so when they do collide and they form, so say we have hexane collides with oxygen, okay? When we get one entity, when we get that carbon monoxide formed, we know that as the activated complex, and that is the maximum potential energy that happens. And so activated complex is what we also call the transition state, where it's moving from one compound to another compound. Okay, a maximum potential energy, if we remember, if we had a hill like this, remember from physics 20, this is all EP, this is all EK, and somewhere in the two is the both. Okay, so maximum potential energy is the most amount of kinetic energy that is stored in the chemical bonds. An effective collision requires the right amount of energy before a reaction can occur. If you don't have enough energy to start that reaction, then it's not going to go forward. It doesn't matter how much you can rub two things together. If it's not the right amount of energy to start it, then it won't stay that way. And so we call that required energy the activation energy. Okay? So the energy required to overcome that activation energy comes from the kinetic energy that the reactants interact. And the other thing that we need to remember from gas laws in Chem 20 is that at higher temperatures, we know that the gas particles move more quickly, and when they move more quickly, they have more kinetic energy. So this is drawing a lot on our knowledge from the gas laws unit. After the reaction, products have a different potential energy than the reactants because they form different bonds. Also, the products will have kinetic energy because they go back into random motion. So if we were to draw an energy pathway diagram, it shows the changes in the potential energy of the chemical system as the reaction happens, and it's done in two different ways, one for exothermic and one for endothermic. So this is our potential energy measured in kilojoules or joules, and this is our reaction coordinate. Okay, if we're looking at an endothermic reaction, we know that it's going to be a step up. So in order for that to happen, there's low potential energy. Those reactants don't want to form a new compound. So there's low potential energy. And then we can make the reaction happen by adding energy into the system. And so what we see is, we see the reactants, then we hit our maximum potential energy, and we end up at our products. Okay? When we look at this line up here, this is our activated complex. Okay? So it's at the maximum potential energy, this activated complex. We know that this distance, this from here to here, is the enthalpy change for a forward or a reverse reaction, however that may look. If we're looking from the reactants to the products, this is the activation energy, so EA, the activation energy. I'm just going to re-highlight this in blue. So activation energy. And so you need to overcome this energy to get to the product. So this is of the forward reaction. Now, if we were going to go in the reverse reaction, if we were going to flip this equation around, start at the products and go towards the reactants, this activation energy would be the energy of the reverse reaction. Okay? If we were to look at it, in exothermic terms, remember exothermic is a release of energy, so our reactants have high potential energy. They're ready to turn into products. Our products are quite happy existing, and so they don't have a whole lot of potential energy. And so what we see is it takes a little bit of energy to happen, and then this energy is released. So again, this is our activated complex. This is the maximum potential energy that's required to make this reaction happen. The net between the reactants and the products, this is our delta H. This is our change in energy. But this height here, from your activated complex to your reactants, this is your activation energy. In the forward. And from your activated complex, from your maximum potential energy to your products, this is the amount of energy required to go backwards to your products. So this would be of the reverse. Okay? Lots of information on these diagrams. This is the maximum, your activated complex is the maximum potential energy that the reactants will have to move into the products. And so in an endothermic reaction, it requires a lot of activated energy to get them to move towards products. If we were to reverse the reaction, it wouldn't take very much energy for these products to change into the reactants. If I looked at an exothermic potential energy diagram, the reactants are more than happy to change into the products. It requires a lot of energy for them to stay as a reactant, so it's going to take a little bit of energy to encourage them to react and move towards move amongst each other and create a product. And these products are quite happy to exist as products, so it would take an incredible amount of energy to change them back into reactants in the reverse reaction. Okay? So we're going to remember that exothermic and endothermic reactions are used using bond energy terms. If we have more energy released due to bonds forming, than energy required for bonds breaking, then the reaction is endothermic. If more energy, I'm going to say released here, if more energy is absorbed for bond breaking than the energy released from bond making, reaction is endothermic. Okay. We're going to skip over this energy activity and we're going to look at how to read potential energy diagrams. So looking at this potential energy diagram, it lists the different levels of potential energy. It tells you that this is a forward reaction, that this is a reverse reaction. And so it says, here's your this here and this here. I should use that. Here's the starting and there's the ending. And so we know that this is our reactants. This is our products. This is a step up energy diagram. And we know that step up energy diagrams are endothermic because they require more energy than they release. So does the graph represent an endothermic or exothermic? It's a step up, so it's endothermic. And it says determine the heat of reaction for this reaction. So it's asking us the heat of reaction is the change in energy, which is delta H. So when I look at energy of the products minus energy of the reactants. I see that I've got 100 minus, right, 100 minus 50 kilojoules. So my delta H is going to be equal to 50 kilojoules, right? We identified that right here. Okay, it says determine the activation energy. Remember, the activation energy for this reaction is the maximum potential energy reached. So we're going to start from 250, or activation energy, sorry, is going to go from the reactants all the way to the activated complex. The maximum energy required, maximum potential energy is the activated complex. So we have 250 kilojoules at our maximum, and we started out at 50. So our activation energy for the reaction in the forward is 200 kilojoules. Okay, that's this piece here. Now it says determine the reverse activation energy. So that's going to be from the products to the activated complex. And we know that the activated complex is again 250 kilojoules. And our products are at 100. So our activation energy in the reverse is going to be 150 kilojoules. And that's going to be what we see here. Okay, activation energy. So you're going to, this is as complicated as it gets. You're going to work on page 420, 2, 3, 4, 5, 6. You don't need to do an energy diagram for number 4. You're going to work on question 9 and 13, and then you're going to work on these practice problems.